In today's video, we're going to look at the latent heat of ice. We have got a balance which we're going to weigh each of these beakers on. So the control one, the initial weight is 3761 grams, and our sample one is 37.43 grams. We've put them under the funnels. Now there's two setups. One of them has just got the funnel, a gauze and a heater, but the heater is not connected to anything. That's our control. The other one is the same, but is connected via a joule meter, which we're going to set in joules, connected to a power supply. We're going to put ice in each of these. Just tilt it up a little bit. About the same amount of ice. It isn't important how much ice goes in them. So we've got about the same amount of ice in each, and I'm going to start the joule meter and switch on the power supply, and you can see the joule meter is recording how many joules of energy is supplied to the heater in this side funnel. We're going to leave that for several minutes, and then at the end we'll record how many joules, and we'll record the weight of the beakers with the water that has melted. So in our latent heat of ice experiment, we're having to make sure that the ice makes contact with the heater, because it sometimes melts it away from the heater. And I'm going to stop it there. We've got to 23 kilojoules. So I'll write down 23 kilojoules, 23.0 kilojoules. But we're going to let the ice continue for a while until the heater has cooled down, because the heater is still hot and it's still giving energy to the ice and still melting it. So 23,000 joules of energy melted 0.04316 kilograms of ice. So if we divide both sides by 0.04316, we will get the number of joules to heat up and melt 1 kilogram of ice. So that calculation comes to 532,900 So that's 5.33 times 10 to the 5. The actual figure is 3.34. So we're not very accurate with this. We may still have some water coming out. We've got too high a figure. In fact, there's still a little bit coming out of that funnel. The heater may still be a bit warm. We will have heated up the surroundings a little bit as well. So there's losses in the heating. We might have run it longer to get a bigger sample. That will have given us a more accurate reading. But we are in the right par of 10. So I'm not too bothered. Also, of course, we've made assumptions. We've assumed the water started at, the ice started at close to 0 degrees, whereas it was probably several degrees under, it was probably about -5 or 6. And we assumed the temperature of the water at the end was only just above 0 degrees, whereas it was probably a bit warmer than that. So there's quite a lot of losses in heating the ice up to 0 degrees, and the water coming out is probably above 0 as well. So that explains why we're quite a bit out with our figures.